Welcome back to my class, Physics for Engineers, and this is the second module of our course. And the topic for today is kinematics. So by the end of this module, the student is expected to number 1, define and apply concepts of average and instantaneous velocity and acceleration. Number 2, solve problems involving initial and final velocity, acceleration, displacement, and time. Number 3, demonstrate your understanding of directions and signs for velocity, displacement, and acceleration. Number 4, solve problems involving a free-fall body. Number 5, describe the motion of a projectile by treating horizontal and vertical components of its position and velocity. And number 6, solve for position, velocity, or time when given initial velocity and launch angle. So, this lesson is part 2 of module 2, and we are going to talk about two-dimensional kinematics. So, what is two-dimensional motion? So the key point here, the only thing that you should remember in this lesson is that motion in 2 dimensions can be modeled as 2 independent motions in each of the 2 perpendicular directions associated with the x and y axis. That is, any influence in the y direction does not affect the motion in the x direction and vice versa. So in this animation that I have, so the stickman throws the ball horizontally, but due to the influence of gravity, the ball it travels in a curved path downward. So in the shape of a parabola. So if gravity does not exist, the ball would have been traveling in a straight line horizontally. But since there is gravity, it will travel in that path, as you can see in the animation. So it doesn't matter if the boy threw the ball horizontally or just straight downward. If he let the ball just drop in a free fall motion, because the time that the ball will reach the ground is the same as when he threw it horizontally. So in a sense, we will the x direction, his action of throwing the ball in a horizontal direction did not affect the motion of the ball downwards and vice versa. So the position vector for a particle moving in the xy plane can be written as, so take note, this is the vector form, vector notation for the position. So R, which stands for resultant, vector R is equal to xi plus yj, in which x is the magnitude of the x component and y is the magnitude of the y component, and I hat and j hat are the unit vectors. So if the position vector is known, the velocity of the particle is established in the last lecture as the derivative of the first derivative of the position with respect to time. So we have dr over dt, which is also equal to dx over dti plus dy over dtj. So that gives us the vector v as vxi plus vyj. So in this figure, as you can see, the horizontal red vectors representing the x component of the velocity are the same length in both parts of the figure, which demonstrates that motion in 2 dimensions can be modeled as 2 independent motions in perpendicular directions. So in dealing with 2-dimensional motion, we just need to understand and remember that you should treat the motion of the component of the object in the x direction as separate and in the y direction as separate. So they are independent of each other. And the resultant of those 2 components is the path of the motion that we can see that in this figure. So we can model the particle as a particle under constant acceleration independently in each of the two directions and apply the equations of kinematics and separately to the x and y components of the velocity vector. Since vxf, or the final velocity in the x direction, is equal to the initial velocity in the x direction vx plus axt, and vyf is equal to vyi plus ayt, therefore if we combine these two equations, we can have the vector, the velocity vector v, which is equal to the sum of the initial velocities, the resultant of the two initial velocities, vi, plus at, which is the resultant of the acceleration in two directions, times t. So, the x and y coordinates of the particle under constant acceleration are, if you need to review this equation on the last module, the last lesson, well, you can. But this formula is just the displacement formula. We just transpose xi here because xf minus xi is equal to total displacement change of x. So xf, or the final position x, the x coordinate of the final position is equal to the initial position plus vxi, the initial velocity, times t plus 1/2 axt, and that's also the same. That also applies to the y direction. So yf is equal to yi plus vyit plus 1/2 ayt squared. Then, therefore, the position vector rf. Sorry, I just forgot the arrow here. And so the position vector is r is equal to xi yj, which is equal to ri plus bit plus 1/2 at squared. So always remember, treat x and y separately. Then if you want to get the total position vector, get the resultant of the two. Combine them like this. So, for the graphical representation, so I have here two figures. So, the graphical representation of the first equation. Sorry, let me look at that. So this is this equation. V is equal to Vi plus At. So suppose that we have the initial velocity vector plus the acceleration vector times time. Then we will get if we want to get the resultant of the two, then we will have the final velocity Vf. So we can break down Vi into x and y components, same with acceleration times time and final velocity. So for the position vector, this is a little more understandable. So we suppose that this is our Ri, or initial position. So Ri plus Vit plus 1/2 At squared. So if we get the resultant of the three vectors, we have the Rf. So we can see that in this equation. So let us have an example. So we have a particle which moves in the xy plane starting from the origin t0 with an initial velocity having an x component of 20 meters per second and a y component of 0 meters per second. The particle experiences an acceleration in the x and y direction given by ax is equal to 3 meters squared and ay 9.8 meters per second squared due to gravity. So we have to make this value 9.81 negative because we treat the downward direction as negative and the upward direction as positive. So determine the total velocity vector at any time. So suppose I have this particle here. So this particle starts from the origin. Then it has so it should be, given our condition, it should move in this manner, just like this line over here. So at any point of this particle, in the path of this particle, there will be x and y coordinates that we have to treat separately. So the question is to determine the velocity vector of the particle at any time t. So let us lay down what we know, the facts that we know about the problem. The initial velocity, the x coordinate at the x-axis, in the x direction rather, is 20 meters per second, and for the y, it's 0. For x, the acceleration in the x direction is 3 meters per second, and the acceleration at the y direction is negative 9.81 meters per second squared. So, using the formulas that we already know, v, or the velocity vector, final velocity vector, is equal to vi plus at. So let us just substitute the given to this formula. So the resultant vector for the initial velocities is xi, so xi plus yj, so 20i plus 0j, plus then we substitute the resultant for the acceleration. So we have xi, so 3i minus 9.81j yj t. So combining like terms, we have 20 plus 3ti minus 9.81 tj. So please take note that when dealing with vectors, just you will combine the terms that have I, then terms that have j. So that's the only way that you should separate the two combined terms. Okay, so separate the i's and j's. So there we have it. So another example, calculate the velocity and speed of the particle at t is equal to 5 seconds and the angle the velocity vector makes with the x-axis. So basically, we will solve for the value of this velocity vector at t is equal to 5. Then we will convert the unit vector notation into the polar notation to get the magnitude and the angle that the vector makes with the x-axis. So using the formula that we got earlier and substituting t for 5, substituting 5 for t, we have 20 plus 3 times 5i minus 9.81 times 5j. So we have 35i minus 49.05j. So this is our vector, the velocity vector at t is equal to 5 seconds. So to calculate the absolute value of this vector or the magnitude, we can use the Pythagorean theorem. We have 35 squared times 49.05 squared, and square root of that, we get 60.16 meters per second for the magnitude of the velocity. Then the angle is tangent inverse of Vy over Vx, and this gives us the value negative 54.49 degrees. So that means that the angle is 54.49 degrees downward, or I mean counterclockwise from the positive x direction. So it points down to the right. So another example, determine the x and y coordinates of the particle at any time t and its position vector at this time. So we solved for velocity for the earlier two examples. Now we solve for the position. So our position vector r is equal to xi plus yj. Rf is equal to xfi plus yfj. And we also know that Rf is equal to Ri plus Vit plus 1/2 At squared. So how do we proceed from this? So to get the final velocity, xf, we have, since we start from the origin 0, 0, xi is equal to 0. So xf is equal to 0 plus vxi plus 1/2 ax squared. So we have xf is equal to 20 times 1/2 times 3 t squared. We have 20 plus 1.5 t squared. Now for the y coordinate, we do the same. since 0 is the we start from 0, and also Vyi is 0. So we have yf is equal to 0 plus 0 plus 1 half times negative 9.81 t squared. We have 4.905 t squared. So combining the two, xf plus yf, we have 20 plus 1.5 t squared I minus 4.905 t squared j. Okay, so we now come to the projectile motion. Well, projectile motion is just two-dimensional motion considering the effects of gravity and considering that the speed in the x direction remains constant. So projectile motion of an object is simple to analyze if we make two assumptions. Number one, free fall acceleration is constant over the range of motion and is directed downward. So in reality, the gravitational constant or the gravitational force of the earth is not really constant, and it varies, depends on where you are in the world, and it also depends on your distance from the core of the earth due to the gravitational law of attraction, universal law of gravitation, sorry. But in this topic, we are going to assume that free fall acceleration is constant and it is directed down. And number two, the effects of air resistance is negligible. So in real life application, air resistance is not negligible, but for the sake of simplicity, we're going to assume that it is. So with this assumption, we find that the path of a projectile, which we call its trajectory, is always a parabola. But in real life, since the shape of the parabola suggests that the earth is flat, but the earth is not flat, so therefore the path of a projectile is not really a parabola, it's somewhat of an ellipse. But anyway, for the sake of simplicity, we're going to proceed with these assumptions. So in this figure, we have the path of a projectile. So the y component of the velocity is 0 at the peak of that path, so we have to remember this. At the maximum height, the y component is 0, but the x component is not. Okay, so the projectile, if the projectile is launched if the projectile is launched at an initial velocity of vi, shown like this. So this is our angle, so it travels in this path, which is a parabola, and at any time the acceleration due to gravity is constant, so the velocity in the y direction varies, but the velocity in the x direction does not. So the x component velocity remains constant because there is no acceleration in the x direction. So we assume that the particle at the same level have the same speed. Okay, so when the particle reaches this level, so let's say A and E, from A to E, so the particle here and at point A and point B has A and point E has the same speed, and from that point downwards it behaves like a free-falling object. So we already know this formula from our past discussion, but Vxi is equal to Vi cosine theta, or the x component of the initial velocity is Vi cosine theta, and the y component is Vi sine theta. In a projectile motion, acceleration at the x-axis is considered 0. On the y-axis, it is equivalent to the gravitational constant negative g, or negative 9.81 meters per second. So, these are the formulas that you need to remember in projectile motion. So, xf is equal to xi plus vxit. So, we already know this. Vyf is equal to Vif minus gt. So this is just Vf is equal to vi plus at, but substitute a for negative g. Then average velocity, you know this. Then yf is equal to yi plus 1 half byi plus byft. Yf is equal to yi vyit minus 1 half gt squared, you know this. Then v squared yf is equal to v squared yi minus 2g yf minus yi. This is just v squared is equal to vf squared is equal to vi squared plus 2as, which s is the displacement. So the horizontal and vertical components of a projectile motion are completely independent of each other and can be handled separately with time t as the common variable for these components. So remember, although you treat the horizontal and vertical components as different or independent of each other, the time is the same for the two. Okay? So if you use the value 1 second for the x component, you also use the same value for t for the y component. So since the projectile motion is already happens a lot, so I mean there are many problems that are modeled by the motion of the projectile. There had been some shortcut formulas that you can remember when dealing with projectile. So we assume that the projectile is launched from the origin at t is equal to 0 with a positive vyi component as shown and returns to the same horizontal level. So this is our vector, and we measure the angle from so say this is the path. So we draw a line which is perpendicular to the tangent to the graph at point 0. So we measure the angle from that. Okay. So to determine the maximum height h at point A, so that's this point, we should take note that the velocity of the particle at that point is equal to 0 in the y direction. In the x direction, in the x direction, it does not change. So vyf is equal to vyi minus gt. 0 is equal to vi sine theta minus gta, and we have ta, or the time that for the particle to reach A, which is equal to vi sine theta I over g. So substituting this value for this formula, we get yf is equal to yi plus byi minus 1 half gt squared, and our h is equal to yf minus yi. So we get vyi v sine theta times v sine theta over g minus 1 half g times vi sine theta over g squared. Sorry, there should be a t here, so vyit. So that's why there's vi sine theta squared here. So combining like terms, you get vi squared sine squared theta over 2g. Okay, so proceeding to the next item, we have the horizontal range. So the range R is the horizontal position of the projectile at the time that is twice the time at which it reaches its peak. So in this figure, this is the R. So as we can notice, the time that the projectile took to reach the maximum point is half of the time that it will span the whole range. So it is just fair to assume that TA is equal to TB is equal to 2TA. So XF is equal to XI plus plus VXIT. So you have R, which is equal to VXTB, since the velocity of the projectile does not change. over time, we have Vxi, which is Vi cosine theta times 2a, which is equal to Tb. So, simplifying terms, we have, since from the equation here, Ta is equal to this, so substitute this here and multiply it by 2, we get this expression. We have 2Vi sine theta cosine theta over g. Then from the trigonometric identities, this is also equal to sine 2 theta. So that is the sum of two angles. So 2 sine theta cosine theta is equal to sine 2 theta times Vi squared over g. Sorry, I also forgot the squared here, so there should be a squared here because Vi here. So Vi squared sine 2 theta I over g. So to calculate for the maximum range, the optimal angle that you can throw a projectile in which it will give the maximum range is 45 degrees. And why is that? Because sine theta, the value of theta that gives this expression sine 2 theta, an answer of 1 is 90. 90. So 90 divided by 2 is 45. So sine 45 times 2 is equal to 1. Then V squared over G remains. So R max is equal to V squared over G. Okay, so I have an illustration here. So the complementary values of the initial angle theta I results in the same value R. So suppose that you throw the ball at 15 degrees, you should not assume that it will go very far. It will just go at a short distance, because sine 2 times 15 sine 30 is such a small value because it's a decimal. So at 30 degrees like this, and at 45 degrees it reaches the maximum range. So when you increase the angle of throw, the range will be equal to the complementary values for that angle. So example, 60 degrees the same as 30 degrees, 15 degrees the same as 75 degrees. Okay, so for an example, suppose that you are this guy Zeke, the monkey, that monkey over there. So sorry if you don't get the reference, just ask your classmate. And you're fighting against squad Erwin. This is Erwin on a horse, and Erwin is Erwin and his soldiers are about a kilometer away from you, and they are charging at the speed of 88 kilometers per hour riding a horse. This is the average velocity of a horse. So how fast should you throw your boulders if you want to hit them? Neglect the difference in the height between Zeke and the soldiers. So if you don't understand the reference, I'll just illustrate the problem for you. So suppose you are this monkey Zeke, and you are 1,000 meters away from the soldiers Erwin. So they're your enemy. So they cannot fight back because you are very strong. You are this giant. So they will just sacrifice themselves by charging at you. So these soldiers run at a speed of 88 kilometers per hour. So you want to defeat them, so you throw boulders at them, but they also charge at you at the speed of 88 kilometers per hour. So how fast should you throw the boulders so that they will hit the soldiers? So since 45 degrees is the optimum angle of throw to get the maximum range, we're going to use this value. So suppose that every throw that you make is 45 degrees. Okay, so let us solve first for the time that the boulder meets the soldiers, or the boulder will hit the soldiers. So at this time, the range R, or traveled by the boulder, and the distance traveled by the Erwin squad from their starting point is equal to 1,000. So going back to the illustration, of course, these guys will move forward closer to you. So you should estimate how fast you are going to throw the boulder, so you will hit them. So the sum of the distance between you and the landing of the landing spot of the boulder and the origin of the soldiers and the distance they travel is equal to 1000. So suppose that they meet here. Okay? So to solve this problem, let us solve first for the time where the boulder would hit the soldiers. So suppose that this is the origin point of the soldiers, so they will travel this far. And suppose that you hit you throw the boulders at just the right velocity, they will reach this point. So they will reach this point. So this will be equal to R, and this is equal to E. So R plus E is equal to 1000. So I have already converted 88 kilometers per hour to meters per second. That is equal to 24.44. If you don't already know how to convert it, just multiply it by 1000 and divide it by 2600. So the range of the projectile is b squared sine 2 theta over g. So assuming that the angle of throw is 45 degrees, we get vi squared over g. So substituting the known values, we have vi squared over 9.81 plus 24.44t. Now this is the formula for constant velocity. So the distance is equal to vt. That is equal to 1000. So this t time is the amount of time that the projectile will take to reach the full range, right? But at the top here, at the maximum height, the time is equal to t over 2. Sorry sa handwriting. T over 2. Now, we want to use other formulas because we are already stuck in here. Because we have vi here and t here, we don't even know what vi and we don't even know what t is, and we're looking for vi. So using other formulas, analyzing the y component of the projectile, we have at the maximum height, vy is equal to 0. So that is this point. Therefore, 0 is equal to vi sine 45 minus 9.81 t over 2. So how did I get this? 0 is the final velocity. Vi sine 45 is vi y minus 9.81, this is g, t. So at the maximum height, t is equal to t over 2. Okay? If the whole range is t, at the maximum height, the velocity, the time is t over 2. So we have vi is equal to 9.81 t all over 2 sine 45. So using the simplifying the formulas, we have 9.81 t squared over 2 times sine 45 all over 9.81 plus 24.44 t, which is equal to 1000. So the time is equal to 12 seconds. So that means at 12 seconds, the boulder will hit the soldiers. So what we really want is the velocity of throw. So we have vi squared over 9.81 plus 24.44 t is equal to 1000. Now substituting the time for 12 seconds, we have v squared over 9.81 plus 24.44 times 12, which is equal to 1000. And finally, the initial velocity is 83.26 meters per second. So how fast is this? The Shinkansen bullet train in Japan is reported to go as fast as 320 kilometers per hour, which is also equal to 88.89 meters per second. While the TGV train in France can reach speeds of about 89.44 meters per second. So that means that the boulders that are thrown by Zeke to the soldiers of Irwin were as strong as being hit by a bullet train.
Well, I don't know about you, but I'd call this mission a complete bust.
Just another day for the Survey Corps.
My entire team is dead!
So that will be all for this lesson. I hope you enjoyed it and see you next time for our next lesson.